Hey guys! In this video, I'm gonna show you something about the completeness of real numbers. So, we know that real numbers and rational numbers are all ordered Archimedean field, right? But what makes real numbers really stand out? What makes real numbers special is that real numbers has a very important property is that it is complete, or the completeness of real numbers. Actually, for real numbers, we have several axioms, and one of them is the axiom of completeness, right? And here in this video, I'm gonna show you the completeness of real numbers, and you may notice that I wrote that it has like 5 phases. Well, what does 5 phases mean? I basically want to show that actually there are several forms of completeness, or you can say completeness of real numbers from 5 different perspectives, and all these properties or these theorems from 5 perspectives, they are actually equivalent, so you can actually get the result of any one of them from others. Okay, so now let's get started. The first one, the axiom of completeness. All these 5 axioms, all these 5 properties or theorems can all be seen as axioms of completeness. You can choose any one you want, but the first one in this video I'm gonna choose is the least upper bound property, or LUP. So the least upper bound property says that if a set A is contained in R, and it has an upper bound, then what the result is it will have a least upper bound, which is the supremum of A, right? I remember I've already talked about the supremum and infimum of a set. So if A has an upper bound, it has a least upper bound, and this property you may check. Actually, it will not work for some rational sets. Well, for example, we have, say, Q. We call it S. S is a set where it contains elements. R, which is elements of rational numbers, and the square of R is smaller than 2. Okay, then this set S has no least upper bound, right? Because you cannot find certain least upper bound such that the element is in S, right? Well, S here is bounded from above, but you cannot find S has no least upper bound in Q, right? What does this mean? This means Q is not complete, right? Because it does not satisfy the axiom of completeness. Okay. So, the next phase of the completeness of real numbers, we call it a nested interval property, or NIP. So the theorem said, let I1, I2 to IN or some others. You can list as much as possible. Be a collection of nested closed intervals, right? So what are nested closed intervals? It simply are those intervals that nest connected to each other. So I1 is I1 contains I2, I2 contains I3, blah blah, until I like n minus 1 contain In and contain until, well, as much as you want, right? Then the intersection of all these intervals from 1 to infinity, the intersection of these intervals will not be empty. So there will always be some elements in the intersection of these nested closed intervals. Okay. Well, as I said, these properties or theorems are different phases of completeness of real numbers. Then I will show you that the least upper bound property can prove the nested interval property. Okay, so how are we gonna do that? The point is, how are we gonna use the least upper bound property? So we are trying to find such a certain kind of least upper bound, right? Okay, so here's a proof. Well, let's denote. First of all, let's denote In by. Okay, let In be An to Bn. Well, here n is, n means for all n. Okay, and well, since I1 contains I2 contains blah 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 to In, it implies what? A1 is smaller than A2, is smaller than blah blah to An, smaller than Bn, smaller than blah blah to, until B2 is smaller than B1, right? So say, well, if I put it on the real line, it's like, well, here's A1, here's B1, and A1, B1, and here's A2, B2. So you are creating the nested closed interval, right? Nested closed interval. And well, let's first consider the set A. The set where all its elements are the lower bound of each interval In. So it's A1, A2, An. Well, for this set, you may say that each Bi is an upper bound of A, right? We know that each Bi is an upper bound for A, right? Because all A is smaller than B. For all AI is smaller than Bi for all I, right? So we also know that A is contained in R, right? Because all these elements are real numbers. Then what we know that A is contained in R and A has upper bound. Then it has a least upper bound, say S. Okay. Well, least upper bound is the same as its supremum, right? So supremum of A is S. And also it is also an upper bound of A, right? So that is to say S is larger than An, right? Okay. And another thing is that, well, since Bn is upper bound of A, right? We just talked about Bn is an upper bound for the set A. So, and S is the least upper bound. supreme of A, so S is smaller than Bn, right? So what we get, in this part we know that S is larger than An, and also we know S is smaller than Bn, and here n doesn't only mean the one specific number, n means for all n, right? So that is to say, for all n, S is contained in In, right? We know S is larger than An and smaller than Bn, so S is contained in In for all n, right? That is to say, S is contained in the intersection of In. Then we've got it. Okay, the next part is to conversely prove from the nested interval property to the least upper bound property. So NIP to LUP. How are we gonna do that? The point is how we're gonna construct the closed intervals, or the collection of closed intervals. Okay, so we'll say we have a set. So we have a set A. A is contained in R, and we choose the first interval. We'll say A is like here. This is A, and we choose the first interval. I naught be A naught to B naught. But how are we gonna choose A naught and B naught? Well, we guarantee that A naught is not an upper bound of A. And Bn is a upper bound of A. Say A naught, B naught. Okay. So this is I naught, and we're proceeding to find we're proceeding to find I1, I2, I3, right? Well, first we notice that I naught intersect A is not empty, right? Well, because if it is empty, we cannot further to find I naught. We cannot further to find I1, I2, right? Okay. Let's say let's see how we're gonna find I1. Well, let's first take C to be the middle point of A naught and B naught. Well, say it is here, and we check if there exists some element of A that is in this part. Well, if there is some point A here, then we set A1 to be C and B1 to be B naught. Or otherwise, if there is not any element in this part, then well, we will take the second interval to be A naught to C. So in this case, the case that I draw in this graph, well, both are okay. You can either take I1 to be like this one or this one. Both are okay, right? Because you can both find some element in that part. Okay, so continue to doing so. What we will get? The general case In will be, well, An to Bn, right? And similarly, An will not be an upper bound, right? And Bn will be the upper bound. I'm sorry, in the previous case, I1 can only be chosen in this part, because we want to guarantee that Bn will always be the upper bound of the set. Okay, so Bn is the upper bound. Of A. I'm sorry. So we are like prioritize this condition if there is some elements larger than if there is some elements in A larger than C, then we take this part. Okay. So what we get, we now know that I naught contains I1 contains blah blah to In, and we also know that An is not an upper bound and Bn is an upper bound of A, right? And by nested interval property, what we will get that actually the intersection of all the intervals In will not be empty, and also we know that the length of this interval In is actually approaching to 0, right? It's getting smaller and smaller, approaching to 0. So the only thing that remained in the intersection will be the single element, say S. So actually, intersection from 1 to the infinity will be a single element, say S. Okay, so next part we're gonna show, or we claim that S is an upper bound of A. Okay. So assume that let's first assume there exists certain element A in the set A such that A is larger than S. And since the length of the interval is approaching 0, what we get, there exists some element M, which is an element of natural numbers such that IM, the length of IM is smaller than A minus S. That is to say, well, in the for the length of A minus S, there will be some interval satisfy this length, right? Smaller than A minus S. And well, since S is contained in IM, S is containing all IN, and so S must be containing IM, and A is not in IM. So A is larger than BM, right? Well, because BM is the upper bound for IM. But this is in contradiction, right? Because BM is an upper bound of A, and if you find some element A that is larger than BM, then it's not possible. BM cannot be an upper bound. Contradiction, right? Because Bn is a upper bound of A. Okay. So, I'm sorry. Here I should claim S is a least upper bound. Least upper bound. So, in this part we are showing that S is an upper bound, right? we are claiming S is in least upper bound, so we first show S is in least upper bound. And how we're going to do that? We, by contradiction, we first assume S is not in least upper bound. So that is to say there will be some element in A that is larger than S. And we know that it's not going to happen. So S must be an upper bound. And the second part is to show that S is a least upper bound. So, well, since we want to show it's a list, then still we let R smaller than S. We show that we want to show R cannot be an upper bound of A. Still by contradiction. We want to show S is a list. Then we assume it's not a list. That is to say, there will be some element smaller than S. But if we can prove that certain element cannot be an upper bound of A, then we can conclude that S is actually a least upper bound. So I'll leave this part to you. It's quite simple. I think I've already done similar job in the supremum and infimum video. Now we move on to the second theorem, which is monotone convergence theorem, MCT. It says that if the sequence AN is monotone increasing or decreasing and bounded above or below, then it is convergent. So well, we will show that the first theorem with the first property, this upper bound property, can deduce the monotone convergence theorem, and this is the third one. And the monotone convergence theorem can prove that the nested interval property is true. So first of all, let's prove the monotone convergence theorem from the LUP, this upper bound property. Okay, say we have a set AN. Let AN be bounded. Then it has a least upper bound, right? Well, AN is the elements of AN are all real numbers, has a least upper bound. Say S. Okay, this is simply the result of the first property, least upper bound property, right? And okay, since S is the least upper bound, then we get for any epsilon larger than 0, S minus epsilon is not an upper bound, right? If A. And also, this also means that there exists n, a number n, which is the element of natural numbers, such that an is larger than S minus epsilon, right? Well, S minus epsilon is not an upper bound of an. So there will exist some elements between S minus epsilon to S, the least upper bound. And since we know that an is increasing, right? So an will be larger than or equal to an, that element in between S minus epsilon to S, right? For for all n larger than the capital N. And also we know that an is smaller than S, right? Because S is the least upper bound, and smaller than S plus epsilon for n, right? So this implies for any epsilon larger than 0, and there exists an n, which is a natural number, such that when n is larger than when n is larger than the capital N, we have an minus s is smaller than epsilon, right? That is to say, an is convergent, and an converges to s, right? So we prove that the sequence, which is monotone increasing and bounded above, is convergent. Okay. Now let's prove it from another perspective, from the nested closed interval to MCT. NIP to MCT. Okay, say we have Bn is an upper bound. It's pretty much the similar construction of the interval. Bn is an upper bound of An. And we start considering the closed interval In. Let I1 to be A1 to B1, where B1 is equal to B. And now we are trying to find the second interval. Okay, now let's first define C to be the middle point of A1 to B1, right? And similarly, if there exists some element AM, well, previously it's A because we are simply taking the elements from the set A, but now we have the sequence AN. So if there exists some elements of the sequence AN, so say AM larger than C, then we define I2 to be A2 to B2, which is C to B1. So that is the A2 is, well, we let A2 to be C and B2 to be B1. Otherwise, I2 will be I1 to C, right? It's pretty much the same. And continue to doing so, we construct such a certain kind of nested closed interval. I1 contain I2, contain blah blah, contain IN. And we also know that the length of IN is approaching 0. So as we previously said, we know that the intersection of IN will be the single element S. And so the next part is to simply prove, or we claim that AN is approaching S. And this is quite easy. So I'll leave it to you to prove that. I'm sorry, I think the sequence, the symbol should be written in this way. I'm sorry. Okay. And the next part, I also want to give you the proof of the monotone convergence theorem to the nested interval property. So let's see it. Okay, now we know that, well, the nested interval is simply how it is. So suppose we've already know that we've already given the nested intervals. I1 contain I2, contain blah, blah, contain IN. And still we choose like so I'm sorry. For ON, RN is AN to BN. Okay, so this implies that A1 is smaller than A2, smaller than A3, blah blah, to AN, to BN, until B1, B2 to B1. Okay, and well, now you say that this sequence A1 to AN to some others is actually monotone increasing, right? The sequence is monotone increasing and is bounded, right? Because, well, each Bn is the upper bound for the sequence. So An is monotone increasing and bounded, right? So by the monotone convergence theorem, we actually know that this sequence is convergent. Right? And we and say An converges to A. So we know that A must be contained in each interval AN, BN, right? Well, because A is larger than A larger or equal to AN, and A must be smaller or equal to BN, right? For each N, so A must lie in AN to BN, this interval for all N. Okay, so A must lies in the intersection of IN, right? So we prove that intersection of IN is not empty, which is simply the nested interval property. Okay,